Welcome to the final lecture in the What is Sound section of our course. Today we're going to talk about a few pieces of audio measurement equipment, and then we're going to talk about acoustics, and that will be related to the speed of sound, the frequency wavelength, but more importantly to the localization and the movement of sound. And then we'll also talk about room acoustics, which will include modes, resonators, absorption coefficients, reverb, reflections, comb filtering, phasing, and flanging. To start with, in our audio equipment section, we are going to look at a sound level meter, or we're going to see one here on the screen, and then we'll see one electronically in the sample. And a sound level meter simply has a calibrated microphone that is capable of receiving all or most of the 20 to 20 kilohertz frequency range. It receives the sound pressure levels in this calibrated microphone, and then you can usually choose between the A and the C weighting for the frequency response. And lower cost units may only include the A weighting because it's more expensive to include the electronics to do the C weighting as well. So the proper settings, if you have the ability to measure either A or C, would be to use the A weighting scale for sound pressure levels up to about 90 dB SPL. And then for sound pressure levels above 90 dB SPL, use the C weighting. And if you remember last week, we talked about the Fletcher-Munson curves or the equal loudness contour curves. That's where the A weighting and the C weighting comes into play. Now, the second piece of gear that we will talk about is a real-time audio analyzer, abbreviated RTA. And the RTA is much more sophisticated than the sound level meter. For all intents and purposes, the RTA is a sound level meter, but it's split up into 32 or 64 or 120 different bands that measure just a small range of the frequency in each one of the bar graphs that you see here. RTAs can be dedicated hardware like the unit you see on the left, or can be software that you run on your computer. And we're going to look at a software version of the real-time analyzer, and you can see as I talk the different levels change. And over on the right-hand side, you see a single bar chart. That is the same thing as the sound level meter that would show. It just shows one unified level for the sound. And over on the left-hand side, you can see the different frequency contents, starting at 20 hertz on the left, going up to 20,000 hertz on the right. So when I talk, you can kind of tell there's a large range of frequencies that are included in my voice. I'm going to try, if I can, to see if I can whistle at 1,000 hertz, and you'll be able to see that on this chart. So I whistled starting at 1,000, and then I swept up to 2,000, which is double the frequency and one octave higher than the 1,000. So I'll go ahead and try to do that again. So you can kind of see how sensitive this thing is. Now, this is one version of a real-time analyzer. Another version of the real-time analyzer looks like this software here. And instead of showing a bar chart, it's going to show at the top the actual waveform. And at the bottom, you can see very rapidly changing content of where or how I'm speaking. So again, if I try to do that 1,000 hertz whistle, up to 2000, you can kind of see that sweep as well. And finally, we're going to, let's see, go back to our presentation. The next piece of equipment is another version of the real-time analyzer, and it is a fast Fourier transform analyzer. And this gives kind of sort of a waterfall view of the sound spectrum, where the color is darker when the level at a specific frequency is lower in level, and the color is lighter when the signal is louder. And to see an example of this, we will go to a website that demonstrates a spectrum analyzer. And this is a bird chirping. And you can see the yellow areas indicate the louder or the stronger waveforms within the bird's chirp. If we look at a violin, when I play this one, you're going to see the fundamental frequency as the lighter color, and then the harmonic series above the fundamental will also show up and be visible. So you can see the larger yellow area at the bottom is the fundamental, and then each of the harmonics are shown above that. And one final demonstration that just shows the fundamental frequency standing out is a police siren. And this is pretty much the audio measurement equipment that we're going to talk about for this lecture. The next section, we're going to move into acoustics. And acoustics is the science that deals with the production, control, transmission, reception, and effects of sound, as told by Merriam-Webster's dictionary. It's basically the science of sound wave behavior in an environment. And acoustics extends far beyond strictly musical or architectural spaces. But in our field, we are primarily focused on those two, but you may find yourself more interested in some of the other areas. And if we look at this chart here, we can see that there are 4 basic quadrants that acoustics falls into. In the upper right-hand corner, we have engineering, which includes things like electromechanical and chemical and architectural. And this is the design of rooms and theater acoustics, shock and vibration in a mechanical or machine setting, and electroacoustics, which includes sonic and ultrasonic engineering. The second section is in the arts area, and that's where we get into the acoustics of music, speech, and psychology. And we'll be talking a little bit about that this evening. And then you've got life sciences as well, which is using bioacoustics and physiology in terms of medicine and hearing and so on. The medicine side would be your ultrasounds and MRIs and things like that. And of course, hearing would be related to hearing aids and so on. And then you've got finally the earth sciences, which includes things like the physics of Earth and the atmosphere. And that would be sounds in space and earthquakes, which are very low frequency, as well as underwater sounds in the area of oceanography. Realistically, these are the areas that fall directly in the realm of this course. So more than half of all of acoustics is a field that you might easily find yourself falling into after you graduate. So acoustics, again, is related to the speed of sound, the frequency, and the wavelength, and the environment of the sound modifies the sound waves through enhancement, cancellation, absorption, and reflection. And reflection, as we'll see in the next couple slides, includes reverb, flutter, delays, and echo. Now, we've already talked about the speed of sound, frequency, and wavelength. So as a review, take these questions and just make sure you're familiar with the answers to these questions. What is the standard speed of sound, or the default speed of sound where we measure it? What is the frequency? What is the time for one period or one cycle at 1000 hertz? What is the wavelength for a 1 kilohertz sine wave? What is the wavelength for a 500 hertz sine wave, or for a 4 kilohertz sine wave? And then what is the wavelength for the lowest frequency we can hear, 20 hertz, and the wavelength for the highest frequency, 20,000 hertz, that we can hear? And again, refresh yourself on those outside of this video. They will be important just to have a working knowledge for this course and for future courses. The next thing we're going to talk about in acoustics, and to me, this is where acoustics starts to get really kind of interesting. And this is what my final project or my senior thesis was on when I graduated with my sound recording degree. I really messed with my professor's mind by creating a recording where he could not tell where he was sitting in the room and which direction the sound was coming from the speakers towards his ears. So the first thing we'll talk about is sound localization, which is related to the direction and the distance of the sound. Since sound travels through the air in time and we have two ears, our brain is able to determine both the distance to a sound source and the location of that sound source. And this localization occurs in three distinct domains. The first one is time, and that's the difference in distance the sound travels to reach each ear. The second one is volume, and that's the difference in volume between our ears. And the third one is the frequency response, or the difference in the tonal quality between our ears. Basically, the difference in distance, if a sound is to our left, then it will arrive at your left ear before it arrives at your right ear, and that distance is less than 1 foot, but our brain can detect the difference. The difference in volume, if you remember the inverse square law, as you double the distance, the sound pressure level decreases to 1/4, and our ears can also discern that difference between the left and the right ear, depending where the sound is in front of us or behind us. And the frequency content is changed by the shape of the ear and the fact that our ear lobes and our outer ears, if a sound comes from behind us, the higher frequencies will be absorbed by the ear shape itself, but the lower frequencies will bend around it. So we can use the frequency content to determine the location of the sound and the placement of the sound around us. The Haas effect, or precedence effect, is the psychoacoustic ability first described by Helmut Haas of our ears and our brains to localize the sound coming from any direction around our heads, but primarily in the lateral plane. Sound reaching our ears at the same time is perceived as being straight in front of us. Sound arriving at our left or right ear prior to the other will be perceived as being from our left or right, and the reception time difference determines the extremity of the perceived placement. It'll be a smaller time delay if the sound is just slightly off center from left or right, and a larger time delay as the sound moves farther to the right or farther to the left. And then, as I said in the previous slide, low frequencies tend to bend around our head due to the length of the wavelength, reducing the accuracy of localization of these sounds, but the higher frequency sounds will be able to be discerned by our brains even if the sound is coming from behind us. Now, vertical direction perception, most of our sound perception is in the horizontal, meaning the sounds are placed in a plane to the left or right or in front of us. We also can hear, to some extent, sounds that are in the vertical direction, but it's most sensitive in the horizontal. In order for us to detect sounds in the vertical plane, our head has to be level, and the difference in height of the sound sources needs to be significant. The sound source needs to be close to us. It cannot be far away. And we detect vertical sound based on the sound hitting our ears directly and the reflections of that sound off our shoulders, our body, and the floor. Since sound in the vertical plane tends to arrive at both ears simultaneously. If the reflected sound arrives first, we perceive the sound as being lower than our ears, and if the reflections arrive later, the sound appears to be coming from above our ears. Now, distance perception is very, very hard at longer distances, and we're only able to discern distance at close proximity, and our brains translate the loudness and delay time of the external reflections of that sound into the distance at which the sound is perceived. If the acoustical reflections are live, meaning there is a lot of them, when the direct sound is fairly close, without visual information, the sound source will be perceived as being in the distance. And that's one way that we can trick our mind. This phenomenon makes it very simple to fool our hearing, to translate close sounds to being distant by adding artificial delay and reverb. Now, the next thing we'll talk about is the Doppler effect. The Doppler effect is that sound that you hear when a ambulance or a fire truck or a police car drives past you, and the pitch of the siren or the horn changes as the vehicle passes by. If the sound source is traveling towards us, the perceived pitch is higher than the original, and if the sound source is traveling away from us, the perceived pitch is lower than the original frequency. This phenomenon occurs because the sound source moves towards us. It compresses the air molecules in front of the source closer to each other, causing the wavelength to shorten, and the shorter wavelength creates a higher pitch. Sounds moving away from us experience the reciprocal effect. And here is an example of the Doppler effect. If I can turn off my pen. There we go. Notice as the horn sounds, it gets lower as it passes in front of us. The next thing we'll talk about, and this thing and the next thing are both related to musical performances. The Doppler effect is one way in which sound is modulated, and that is basically just the sound dropping in pitch as the vehicle travels away from us. Another source of modulation is a fan. And if you think of a ceiling or a box fan and you talk or hum into it, you will notice the amplitude of that sound as it reflects off the blades changes in relation to when the blade is closer or farther away from you as the fan spins quickly. And the tremolo, the word is Italian, and there are two types. One is a rapid reiteration of a single note, for example, a bow moving back and forth or a string being rapidly picked on a stringed instrument. And the other one is a variation in amplitude. Note, guitars with tremolo or whammy bars are actually bending the pitch. Even though it's called a tremolo bar, it is not. tremolo. It's actually vibrato, and we'll see that in the next slide. But here is an example of tremolo. And if you notice this, we are hearing the sound get louder and softer. And you can hear this on the sustained notes where it sounds steady and then it starts vibrating. That's the tremolo effect. The next thing we'll talk about is vibrato, which is also an Italian word. And this is a musical effect where instead of a regular pulsating change in amplitude, there's a pulsating change in pitch, which is added to a sustained notes. And two components of vibrato are the extent of the pitch variation and the rate, which is the speed at which the pitch changes. Vibrato adds warmth to sustained notes, especially with voices and stringed instruments, which tend to be very directional. And the added vibrato causes changes in that perceived directional pattern as it interacts with room acoustics to add interest to the sound. And here's an example of vibrato, and this is a very tacky recording, and I apologize.
This is a breathy tone and chest focused note from the heart to you. This is a breathy tone and chest focused note from the heart to you.
Okay, enough of that. And here is a graphical representation of the difference between tremolo and vibrato. And if you notice the words on the right, AM and FM, the amplitude modulation, the changing of the amplitude where the frequency stays constant, is the same way that AM radios work, but at a much higher frequency range. And the bottom one, where the frequency changes repetitively, this is frequency modulation, and it's the same way an FM radio operates. The next section we're going to talk about is room acoustics. And room acoustics is a study of how sound acts in an enclosed space. There are two factors at work when sound exists in a room. One of those is reflection. When a sound wave hits a surface, it will reflect, changing its direction. And when the room has sufficient size and the reflections are far enough apart to be heard as distinct echoes. For a smaller room, it's heard as reverberations. And then the second factor related to room acoustics in an enclosed space is diffraction. And this is the change of a sound wave's propagation to avoid obstacles. Huygens' principle, when a sound wave is partially blocked by an obstacle, the remaining part acts as secondary waves, and the sound escaping a room through an open door would be an example of the secondary waves. It may not be the entire sound that leaves the room, but part of it. Most rooms have 6 walls, and the walls are typically parallel. So you've got the left and right walls, the front and back walls, and then the ceiling and floor walls. And the frequencies in these rooms are very predictable based on wavelength and the frequency of the sound. So standing waves or flutter echoes happen in rooms with highly reflective walls, and the sound pressure along the parallel walls will enforce itself. And rooms as a whole tend to resonate in the same fashion as a drum. So they have that thump that dies away over time. Now, to look at room acoustics, if we assume that we have 2 parallel walls and we're looking at part of a sine wave here, if you notice that's 1/4 of the sine wave, looking at the left picture on the upper left corner, F1, and just look at the darker colored line. The darker colored line being higher than the neutral center point is showing a compression zone. In the middle of the room, it's at equilibrium or atmospheric equilibrium. A 180 degrees part of the wave is the wall on the right, and that's the rarefaction zone where the air molecules are spread further apart. Then the sound reflects off of that wall, and we're now seeing the lighter colored wave of the same upper left picture. And we are now at a reflected compression zone. And then in the middle of the room, we're at the equilibrium. And at the left wall, we are back at the rarefaction of the reflection. So looking at this, if you were standing at one of the walls of the room, the sound would sound twice as loud, and in the middle of the room, it would almost be non-perceptible. And this is assuming a sine wave with just one frequency. The other way that that same waveform could act is the picture in the upper right. And if you double the frequency, you now end up with two of those equilibrium zones in the room. If you triple the frequency, you end up with 3 equilibrium zones. And these are important to be mindful of when you're putting microphones in a room to record instruments, because the instruments will act differently depending on whether they're in the compression, the rarefaction, or the equilibrium sections or zones of the room. Now, in these rooms, if we look at the equations here, you've got the wavelength of the width of the room, the wavelength of the length of the room, and the wavelength of the height of the room. And in each case, the wavelength is 2 times the height, the width, or the length of the room. And then the frequency of each of those harmonics, the first harmonic of the room mode is the speed of sound divided by the wavelength. And then additional harmonics are multiples of that, just like when we saw the fundamental and then the harmonic frequencies in the first lecture, 2 times, 3 times, 4 times, or 5 times that initial frequency. And that's how to calculate what those room modes are. So if we look at this room here, and for sake of time, I'm not going to go through all of the examples or all of the calculations. But if we were to look at, let's say, just the width of the room, and let me turn my pen back on. So if we were to look at just the width of the room, we have the wavelength is equal to 2 times the width of the room, which is 22 feet, which is equal to 44 feet. Those do not look like 4s. Pretend that they're 44s. So then we take the fundamental frequency, or F1, is equal to 1130 divided by our 44 feet, and we end up with a frequency of 25 hertz, rounded to the nearest whole number. So if we were to calculate, F1 would be 25, F2 would be 50, F3 would be 75, F4 would be 100, etc., and then redo these calculations for the remaining length and height of the room, then we could generate a table that would look like the table here on the left. And if you look at the W in the middle column, that's what we just calculated. Now, the point where you've got 2 of those modes, in this case, the 2 yellow numbers, the width and the height of the room, being very, very close together, those are problematic frequencies in this particular room. And then the 2 blue frequencies would be problematic as well, because they're very close together in frequency, and the 3 red numbers. Now, this being said, do not worry about memorizing these equations or any of these calculations for any of the quizzes or the exams. They will not be on the exams. This is just so you have an overview of this concept of problems with room modes. Now, going back to the previous slide, if we look at our room, and I'm actually going to go back to this slide. If we look at this room and we could place obstacles in the room that could counteract some of these compression zones or rarefaction zones, we will talk about a thing that's called a Helmholtz resonator. And the Helmholtz resonator is a container or a tube designed to resonate the enclosed air at a certain frequency. And the simple example of this effect can be observed by blowing air over the narrow opening of a soft drink bottle. The air in the larger body of the bottle will resonate at a specific wavelength based on the size of the bottle. Your brass and woodwind and organ pipes function in the same principle by blowing air over an opening to make the tube or the cavity resonate. And the same principle can be applied to reverse the resonant frequencies in a room by putting slats on a wall with a sound transparent fabric behind those, and then behind that sound absorbing material and an air gap, and then finally you end up reaching the wall. And that will tend to, and these are tuned, by the way, to specific frequencies based on the size of the openings of the slats and the size of the compartment between the slats and the wall and the amount of absorbing material. So you can counteract the frequencies in the room by generating the opposite of those frequencies at the wall, which will cancel out the resonation. Absorption coefficients are numbers that are assigned to every material, and every material that's subjected to sound waves will react to those waves by either reflecting the sound, vibrating based on the sound, partially absorbing the sound, or transporting those waves to another surface or another location, such as a wall, transporting them to the outside of the wall. The energy that is lost in any of these actions is called absorption, and it's mostly caused by the Helmholtz resonator effect of the pores of every material. The absorption coefficient is a value between 0, where it's totally reflective, and 1, where it's totally absorptive. And an example of 1, total absorption, would be if a sound were to leave through an open window and travel infinitely away from you, so it never ever reflects back. Ironically, that open window is a 100% or has an absorption coefficient of 1 because effectively it totally absorbs the sound. Now, if you close that window, then you would have very close to 0 because glass is a very reflective material. And the thicker the glass, the more reflective it is, because thinner glass will vibrate and partially transport those waves to the other side of the window. Wallace Sabine came up with this concept, and he had originally started a database of these absorption coefficients in 6 different frequency bands. And therefore, 1 square foot of 100% absorbing material or 1 square meter of 100% absorbing material, the coefficient is named after him, and it's imperial if it's measured in feet, and it's metric if it's measured in meters. And the frequency bands that he concentrated on were basically 1 octave apart in the area where human hearing is most sensitive, from about 125 hertz, which is actually a little lower than our sensitivity, up to about 4,000 hertz. Sabines are used to calculate the reverb time within a space, and by summing each surface area multiplied by the absorption coefficients of the materials in that area, you can get the reverb coefficient. To describe what reverb is, if you go into a room such as a commercial bathroom where the floors, walls, and sometimes the ceiling are all tiled, if you clap, once you clap, you'll hear the snap of your hands hitting together, and then you'll hear kind of a psh, kind of a noise. That is reverb. And reverb is when the sound reflections are very equally spaced and very close together, and that would be in a smaller room. The amount of reverb in the space is determined by the duration of that reverb decaying in level by 60 decibels, and it's typically called the reverb decay time, or RT60. A reflection is when the delay time of the reflected sound is greater than 10 milliseconds. And if you listen to the reverb, that would be way less than 10 milliseconds. 10 milliseconds, we start perceiving each one of those reflections as a separate, distinct sound from the original sound. And that rapidly repeated, usually between two parallel surfaces, is called flutter or flutter echo. And that almost has more of like a kind of a sound to it, because it's happening far enough apart where we can hear it. And that is very non-preferred in a recording studio. You do not want flutter echo in your recording studio. Reflections with longer delay times between the initial sound and the reflection, even longer than the flutter echo, is called just plain echo. And echo is basically when you hear the sound go bop, 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 as it dies away, you can distinctly hear multiple copies of the sound. And this would be maybe if you were standing between two buildings that were fairly distant, you could clap and then hear the sound as it reflects off of the buildings back past you before it hits the other building. Dispersion is the last thing we're going to talk about in the dispersion or the spreading of the sound, and that is a total random unidirectional reflection of low to mid or high frequencies. And this is normally achieved by omitting parallel surfaces. In most recording studios, the walls are not parallel, and the ceiling and the floor is not parallel to itself either. And also by dressing the surfaces with uneven slats or pieces of wood or spherical objects. And this treatment in most cases causes a very bright and open sounding acoustic environment with bright, short sounding reverb. And when I say bright, mostly in the higher frequencies, not the lower frequencies where it would tend to sound rumbly. And very often this is partially used along with sound absorbing materials to create a relatively dead room for recording purposes. And then you can add reverb, echo, and other kinds of effects to it to create the type of room you want the sound to be in. One of the bad effects of putting microphones in the wrong place in a room is something called comb filtering. And comb filtering is caused when signals that are identical but have phase differences create regular peaks and troughs in the frequency response when they combine together to either strengthen or decrease the actual sound amplitude at that particular microphone that's picking them up. And the short delay combined with the original sound source creates tiny phase differences, causing frequency coloration over the entire frequency spectrum. And these repeated dips spread at regular intervals similar to harmonics over the entire frequency range, and they resemble a cone. And here is an example of what this sounds like.
Let's start with comb filtering caused by reflections. The sound from this speaker takes two paths to the microphone. A direct path from speaker to microphone, and a reflected path from speaker to wall to microphone. The reflected sound travels a longer distance and will reach the microphone slightly later than the direct sound. Listen to the way the comb filter changes based on how far away the wall is from the speaker.
Interestingly, I have 2 dogs, and when I take them for a walk in the morning, if I bend over and get closer to the ground as an airplane flies over, I hear that same effect of the sound of the airplane because the distance between my ears and the ground is changing, and that is actually a Doppler effect that creates comb filtering because my head is moving closer and farther away from the ground. So if you want to look really weird to people around you the next time a plane flies by, just kind of bend over and stand up quickly a bunch of times and listen to the change in the frequency of that plane flying by.
Let's start with comb filtering.
Okay, let's not. Let's go to the next slide. Here is an example. If you look at the frequency response chart on the right, you can see the original recording and then the comb filtered version of it down below, and you can kind of see the jagged edges, and that's where it gets its name from. The next thing and the last thing that we're going to talk about is an effect of comb filtering that is created deliberately, and it's called phasing or flanging. And for those of you that play guitar, you can get phase or flange pedals. And the longer delay times that are clearly audible as delay or echo do not exhibit the same frequency cancellation effects. But the interesting thing about this is this effect was contributed to a guy named Ken Townsend, who was one of the recording engineers at Abbey Road Studios in London, and that's where the Beatles recorded all of their music. And in 1966, as they were playing a tape, he brushed by the tape deck, and the flanges are the metal reels that hold the tape in place when it's on the tape deck. And he brushed up against that, causing the flanges to change speed. And immediately, that became an effect that they started using in recordings for music. The initial idea was used by John Lennon to create an effect that sounded like Lennon had recorded his voice twice, which was the common way back in the 60s to thicken a voice track. And then the concept of automatic double tracking was born. In order to create this desired delay, you slow down one of the tape recorder's playback speeds by pressing your finger on the flange or speeding the flange up until the desired delay was achieved. And the phasing, that's the automatic doubling, but the process of speeding up and slowing down is where you get the phasing or flanging effect. And if we looked back at the previous slide where we saw the comb effect, the comb tongs or tines or whatever would be moving up and down as that tape was changing speed from one speed to another when you put your finger on it or speed the reels up. Lennon called this comb filter effect Ken's flange effect, and the name flanging stuck. And this effect was first used by the English group Small Faces on their Itchy Coo Park album. And for all intents and purposes, comb filtering, phasing, and flanging are inherently the same thing. Here is an example of this being demonstrated. So this guy is going to start the second version of the song and then speed it up until it matches. And then he's going to touch the left reel to slow it down slightly. And you can hear the sound kind of swirl, and then he'll speed it back up by turning the right reel. And the engineer liked it, and here's what it sounds like. And if you noticed in that recording, it kind of had a swirling effect to it. That's the phasing or flanging effect. And that concludes this video. And I apologize for the length. But good luck. And again, don't worry about those math equations in the middle. They will not be on this week's quiz, and they will not be on any of the exams. And then later on in this week, I will be putting out a study guide for the exam. And the exam is going to be very much like the quizzes you've been taking, just a little bit longer and using different numbers and trying to teach you the concepts and the theory by thinking as opposed to just memorizing. And good luck.